we heard there's some introductory materials, and this is a book that a very short thing that Jim Feng and I wrote together 3 years ago now. And it was particularly for students and the researchers with a math background, but hopefully for physics and chemistry readers, they can find some of the discussion clarifying too. See more references by Jim Feng's talk and Alexander's talk on Tuesday. It contains a lot of useful information. I very much appreciate that Robert gave a talk containing an excellent introduction of second quantization that makes my job a lot easier. And I also want to advertise this paper. It was a tutorial or perspective paper on the International Journal of Quantum Chemistry by Saleh, Reinhold Schneider, Ola Lagaza, and Tensor people, but has about 10 pages or so on the materials, on the numerical aspects of second quantization. I read a lot of this morning. I asked Kiran about what's a good textbook on the numerical aspect of second quantization. The textbook, really, there are a lot of textbooks talking about those, but numerically, there are really not that many. And I really learned a lot from this paper. Okay, so first to give a crash course on second quantization, which is really needed. It wasn't. You can argue that it's not necessarily so much needed for DFT. It will make some of the calculations easier, but for quantum embedding or for tensor methods, they're really, really crucial. And they're not that hard either. So you think there are L size, which are called spin orbitals. There is something called occupation number basis, which means that for each side, you can pick, this morning we heard plus or minus, or 0 or 1. So all of them, you can choose 0 or 1, so this is a basis of size 2 to the L. You give it an inner product, which means that only if all of them agree with each other, they're all 0 or all 1, you get 1, otherwise you just get 0. So this is the orthogonality condition. The span of this is the Fock space, dimensions 2 to the L. There's something called a vacuum, often called 0, just means everything is 0. A quantum state in the Fock space is a linear combination of things in the occupation number basis, which means that you have a vector in the Fock space. You can be linearly, these are the coefficients, just a vector in C2 to the L, and in this occupation number basis. And because of the orthonormality condition here, the normalization condition of a vector in terms of L2 norm is just the discrete L2 norm here, just to sum up the square of the numbers, and that is equal to 1. Is that clear to everyone? Okay. So now talk about operators. You see a lot called annihilation, creation, and number operator. You only need to know 2 of them because of the number operator is just A dagger times A. The most important thing is each of them is a sparse matrix of size 2 to the L. That's all you need to remember for the rest of the talk. Okay, so you can work it out, but in the end, it's a sparse matrix. You can work with those. It's not some abstract stuff. In physics, there's something called the Jordan-Wigner transformation. Mathematically, you're just writing down the matrix elements of it in the basis. So this is just to let you know that it can be written down. Either you already know it or it doesn't make any sense to you, but I just want to say that these are the matrix elements in the basis. You can verify that if you take this basis, computational basis, S1 to SL, these are just applying creation operators one by one. If S1 is equal to 0, you don't apply anything. Otherwise, you apply the A1 dagger, apply to the vacuum, and you get the whole basis. There is something called the canonical anti-commutation relation, which means that the anti-commutation means that AI AJ plus AJ AI, and this is equal to 0. And for these things, they're equal to 1 if I is equal to j, or otherwise it's equal to 0. So this is just some algebra that can be derived from the definition above. The total number operator is just the sum of all the number operators. quantum antibody problem in the second quantization is the following thing. We heard it this morning from Rob Weber. You might need to derive 10 pages from Szabo and Oslan. In the end, you end up with something like this. Yeah?
So these creation annihilation things that you talked about there, the L stays the same or L changes when you...
L is a fixed number. Let's say 50, that means you have 50 orbitals.
So when you apply this in P, you stay with the same number of sites, right?
Yeah. So this is always a vector in C to the 2 to the L. Yeah. Okay. So the non-interacting one, or called the quadratic Hamiltonian, is very, very important. I'm going to talk about why it is important. Is that this is summation Tij, Ai dagger, Aj, and then you have a quartic Hamiltonian, and that's it. And you might think, shouldn't all Hamiltonians look like that? No. Because in nuclei, for example, Hamiltonians, and you can have 6 of them, 8 of them, 10 of them, you make a model. But in condensed matter, the quantum chemistry, we have this luxury that we know that the Schrodinger equation just involves 2-body interaction. In the end, you have up to a quartic Hamiltonian, and that's it. So this can be treated. This Hamiltonian, although it contains discretization error, for the rest of the talk should be treated as exact. That's the uniqueness. So the ground state is defined as following. You solve the following linear algebra problem. So I have already defined this total number operator n, and I just defined the Hamiltonian. I would like to pick a number, mu. I'm going to explain that later. Let's say now mu is picked. Then I want to solve this minimization where the vector is taken from the Fock space and it is normalized. Okay, so this is a big matrix. And this is a vector, so just an eigenvalue problem. What is this mu? It's called a chemical potential. It is whenever you see a chemical potential, it must be a Lagrange multiplier corresponding to something. Here it is the Lagrange multiplier chosen so that for a specific number, it's an integer, number of electrons, Ne. This Ne, this morning we had the question, must be a number between 0 and L, so that the average of psi with respect to the number operator is the number of electrons. And you can always tune mu so that this is satisfied. So without loss of generality, we can set this mu to be 0. And but when it's not the case, I'll mention it. And this mu condition can also be relaxed by restricting to the Ne particle sector of F, but let's not forget about it. Let's forget about this for the rest of the talk. That's just making the calculation more efficient. Any questions so far? Yeah.
So does living out the n in that way by setting mu to 0 have any sort of consequences, or
no? Because n is a
but we don't care about.
No, the reason why I can set mu equals 0 is because n is a quadratic part. So it just means that I already know the value of mu a priori and absorb that into T. Yeah, good question. Yeah, the rest of the talk won't be so clear. So it will be good if I ask questions. Yeah. Okay. Yeah. Yeah.
So what? Can you remind me again? I think I forgot it already. So how do you get to this from the actual many-body Hamiltonian? Like, what if? Do you need to make any assumptions, or is this actually exact? Like, what do you need to? What are you throwing away on the way?
Let's just think this is exact. Forget about it.
Forget about it.
Yeah, this is the thing and the only thing you should care about for the rest of your life. So
but you have a fixed number of orbitals.
Yeah. So you have some discretization, you have some rules, and blah blah blah.
So if we take the number of orbitals to infinity, we would be perfect.
Yeah. If take the continuous spaces limit, this is solving the same quantum antibody problem.
Okay, that's all I wanted to say.
Okay, very good. So the simplest setting is this so-called non-interacting system. It is very, very important for many, many reasons. And so this means that the quartic part is thrown out for whatever reason. So you're only left with the quadratic part. Then you can do this linear algebra operation. You can diagonalize this matrix T, which is only of size L. The cost of that is L cubed. So here I write down all the eigenvalues epsilon and eigenvectors psi, so that their eigenvalues are ordered non-decreasingly. Because my assumption of mu equals 0 means that there will be NE number eigenvalues that are below 0, the rest are above. I assume there's a gap here. And if I put all the eigenvectors as a matrix, it is a unitary matrix because T is Hermitian. Then I can do a so-called basis rotation. I define a set of new creation operators through this rule using these coefficients so that the CK dagger is summation AI dagger phi k, and CK is this, but with this complex conjugate. Then do a little bit of algebra. You will find that this H naught is written as just epsilon k with respect to some number operator, but with respect to the k. And these CKs are still legitimate creation and annihilation operators. You can prove that they satisfy the canonical anti-commutation relation. It's not that obvious. You cannot do this on the fly, but I just say this is true. Because of this structure, you can immediately solve that eigenvalue problem by hand. And you find the ground state is just you fill all the first NE orbitals. That is the so-called Aufbau principle applied to the vacuum state. And the ground state energy is just can be written down as the sum of the first NE eigenvalues that are below the chemical potential. This is also called the quadratic Hamiltonian because it's a quadratic, called a single particle picture. There are actually still multi-particles. It's just that these particles don't interact with each other except through the Pauli exclusion principle, which means that you have to fill one by one. Okay?
Just a short. So the Pauli exclusion principle is here because even though we don't have the determinant, we kind of think in terms of spin, right? So
these are spin orbitals.
Yeah.
So another important quantity is called single particle reduced density matrix, or 1RDM. So it is observable in the sense that give me any quantum state. It doesn't need to be non-interacting, any quantum state. I can define this matrix called the Dij to be the average with respect to AJ dagger AI. It's not a Hermitian operator, but I can define this quantity. It's not, this AJ dagger AI is not a Hermitian operator, but it will return a number, and this D, you can easily prove is a Hermitian matrix. It's a little bit confusing. Of size L by L is a matrix. The electron density that we have heard a lot in the past 2 days, in this setting is just the diagonal of this guy. Or you can write down as the average with respect to now a Hermitian thing, Ni, or you can just write this down clearly. So give me any quantum antibody state, this is a well-defined number. The non-interacting system, this Dij has a particularly simple formulation. Let me write that down. So this is the many-body ground state, and remember these are, this phi here is all the occupied orbitals, because only the occupied ones matter here. Then you can follow the canonical anti-commutation relation and first evaluate this quantity called d tilde, which is with respect to this creation annihilation operator of the rotated thing, this CK, called the molecular orbitals, by the way. Then you will find that it's just a diagonal matrix. If this K is smaller than NE, you get 1, otherwise you get 0, because you only have created things below the chemical potential. And yeah. Then you do a basis rotation. You will find that this Dij is equal to this number, which is phi dagger. This thing you might have seen for many times in DFT, in Hartree-Fock, but this is how you get it from a many-body derivation. So the density 1 RDM is just your occupied orbital times its dagger. Okay, recovers that result. A few remarks. For non-interacting system, because D equals to phi dagger, D squared is phi dagger, phi dagger, phi dagger phi is identity, so D squared equals to D. This is called idempotent. Very, very important. Of rank NE. The eigenvalues are either 0 or 1. 2, is D is uniquely defined, determined by phi. Obviously, you give me a phi, and the phi dagger defines D. But give me a D, I can perform an eigen decomposition of the matrix that uniquely defines phi up to a rotation. This is really a feature for non-interacting system, that the whole thing is defined by its one RDM. For interacting system, this is not idempotent, and generally D cannot be used to determine the many-body ground state. Okay, some remarks. This is the first part. Any questions so far? Yeah.
Sorry, a stupid question. I didn't understand what the CIK were.
CIK.
This one, two indexes. Where did you define those?
This guy?
Yes, yes.
Oh, these are yeah. So this is the eigenvector, and I is the ith element.
Okay, thank
Yeah.
you.
Yeah.
Is there any difference between the single particle reduced density matrix from what we previously called the density matrix?
There's no difference. But some people, sometimes there's the n-particle density matrix. We haven't encountered that in this workshop yet, but yeah. So far, the same density matrix. Good question. Yeah.
So when you set up your assumptions before, you had like monotonically non-increasing stuff, but then you had a gap, right?
Yeah, the gap. Yeah.
You have
yeah,
to
yeah.
have the gap, right?
Right. Yeah. Otherwise, you
Everything
need to
sort of falls
think. Yeah.
apart.
Right.
Yeah.
Yeah. But for the rest of the talk, I will. Whenever there's a possibility to simplify the discussion, I simplify it.
Okay. Great.
Okay. So, okay. Next, something we just heard: quantum impurity. What is quantum impurity? So this is really the next simplest setup from a many-body perspective, which is quantum impurity. I can consider there's a graph, okay, and I can put this L size into a graph. And let me show this graph here. This is my best drawing possible. So there are L sides, and some of the sides that are connected to each other. And only if there's edge, Tij is not equal to 0. I can always define a matrix like that. I also want to define a subset of vertices. Let's say, without loss of generality, we say the first M vertices. Those things, there are quartic interactions. Certainly not general. I mean, for general quantum many-body problems, just a click is a full graph. But to make it simpler, I want to say that the quartic interaction only happen to indices with respect to a subset of the vertices. There L is 50. I say there are 3 of them. I allow quartic interaction among them. The rest, they are quadratic. Okay? The quadratic can be arbitrary, but the quartic thing must be restricted to a subset. This is called the quantum impurity problem. So without loss of generality, I think the first M of those has quartic, rest quadratic. Quadratic can also happen between this and that. Yeah. So this is what I mean. H1 takes the form ijkl from 1 to m only. M is much, much smaller than L. Example, my favorite acronym, single impurity Anderson model, SciM, which is the community I belong to. Society for Industrial and Applied Mathematics for those who are in physics and chemistry. And this is the single impurity Anderson model. So there you see some of C and F. The important thing is that this is the only quartic guy, F. The rest are C. So if I define my creation operator to be F dagger, C dagger, the only thing, the quartic interaction happens to be the first degrees of freedom, or first 2 degrees of freedom because of spin. The rest, quadratic. And the quartic can couple with quadratic. Make sense? The number of electrons in the system is generally order L, or theta L, if you want to be rigorous, which means that this thing is not like an impurity problem means there are very few electrons. No, the number of electrons in the system can still go to infinity in the thermodynamic limit when L goes to infinity. This is the setup. Okay, you have a very big lattice, you have a lot of electrons. The only assumption you have is that the quartic interactions are restricted to a small number of sites. Is the setup clear? This is the amazing theorem. This got cut a little bit by Bravi and Cosette in Community and Mathematical Physics in 2017. To my knowledge, that's the first time people actually say something definitive about the complexity of this problem. These are generally theoretical computer scientists. I want to say that this paper significantly raised my respect for the theoretical computer scientists because they not only showed a useful result, they also provided a very useful line of thinking about algorithms. This is I highly recommend it. It's long though, but it's quite a serious paper from both algorithmic and theoretical perspective. It's a very good paper. They say that the complexity, upper bound of it, for estimating the ground state energy E up to precision gamma is this. So what is that? So there is a pre-constant, which is L cube. For theoretical computer scientists, any poly L, they are satisfied, but now it's L cube. And here, it is multiplicative to an exponential factor to exponential OM. That's not surprising, because even if you have an interacting system with M size, that's like of size 2 to the M, so exponential to the M is expected. But the non-trivial thing is that even when you have this many electrons, you can still solve this problem to precision and logarithmic with respect to this. Here's the thing. It's not logarithmic. We can talk about more. Yeah, that precision thing is pessimistic from a theoretical perspective. But for fixed precision, the cost will be exponential to the impurity size times L cube. Rather than if you put this whole thing to Fusei, the cost will be exponential to the L. Does it make sense? So this is just an algorithm with a provable error bound. In practice, if you use some other much better quantum chemistry methods, it will only be better. But it is comforting to know that this problem is easy, is indeed easy to some extent. That is why quantum impurity problem, quantum embedding theory, as Dominika just said, try all possible ways to shoehorn a true quantum antibody problem into these impurity problems, because it can be solved. So the high-level idea of quantum embedding theory is the following. I have a full interacting system. Everything interacts with everything. This dot means that there is a quartic interaction among those vertices. There are only 4. I can be 40, it can be 400. I divided them into few chunks. Each of them, I restrict the interacting part to only be within a subblock. It can be one vertex, it can be a few, but just a small part of it. So each of them is an impurity problem by itself. How do I define it is not clear at all. But I just somehow, at a high level, I want to divide this global system into a few systems here. The assumption, of course, is 2 to the L is too large to be solved, but each of them, I can solve them individually. I'm willing to solve a series of problems, even self-consistently, of size with the impurity size M, much smaller than L, and the cost is up to this much. Often, this is actually pretty expensive if you think about it. The methods that are used in practice, like the Dominika, they're more like, instead of multiplicative, it's more like additive, or even just without that. But I won't talk about this kind of things here. These quantum embedding theories, as far as I know, almost all of them, they're more of a recipe than a rigorous theory, which means that usually there are some extreme regimes, such as non-interacting system, or in DMFT is justified in the weird limit of the coordination number go to infinity or something, which is infinite dimension, but it's not that much related to actual materials. In some extreme regimes, you can justify it, but in general, it's very hard to say anything rigorous. Variational, no. So it's hard. Some examples. Dominica said that, so I will go through that very quickly. Dynamical mean field theory. Density matrix embedding theory is something I'm going to spend a lot of time on it, partly because Dominica has already talked a lot about this SET and DMFT, and I don't think I can do better, and partly because we actually worked on that, and so have some mathematical understanding that is shareable. Tom Miller has a projection-based embedding theory, but many other DFT-flavored embedding theory exists as well. Julia Galli has this constrained RPA-based embedding. And yeah, with Mike, we came up with this variational embedding theory, still in print in Communications of Pure and Applied Mathematics. And recently with Yuhao Ku from Chicago and Michael Lindsay, they had some very nice extension, making it much more feasible for larger problems. And there are many more improvements and many more theories that's summarized in this review paper by Sun and Chen, just called quantum embedding theories in this ACR in 2016. Of course, there have been many more developments since then in the past 6 years. There are some shared commonalities among these quantum embedding theories. They all involve a so-called high-level solver. You hear this ubiquitously in quantum embedding theory. High level just means that it is somewhat close to the solution of the full CI. That's called just the definition of high level. You can solve that impurity problems accurately with a cost up to this. There's a low-level solver. Low-level just means something that's far away from full CI, usually closer to Hartree-Fock, perturbation theory, GF2, whatever things that you heard before. And this low-level solver is going to be applied to the global system with L size. And usually this is a non-interacting problem, but it's not necessary. And the cost for sure will be poly L. It's just something you know is going to be solved with a polynomial scaling, hopefully L2, L3, L4, instead of L to the 48 something. So, and it provides some sort of environmental information to the high-level solver, deliberately vague language. So then you assemble the quantities from the high-level solver, like you assemble all the self-energies we just heard from the previous talk, to obtain a global quantity. You usually don't have the entire information of the global quantity because you just have access to some impurity, some diagonal blocks, something like that, of the global quantity. Then, in order to do it self-consistently, there is a part called a matching condition, which means that these high-level quantities or solvers, they must extract something useful from the low-level garbage so that the high-level things will become more accurate and take into account of the information from the environment. And this usually results in a Lagrange multiplier. For example, the DMET, the Lagrange multiplier, is something called a correlation potential. And Dominica didn't use this language, but the hybridization matrix is basically a Lagrange multiplier in DMFT. But there it's just with more structures.
So is this achieved iteratively or?
Yeah, this is going to be then done iteratively. Yeah. Okay. So some perspectives. Usually these things, the energy and matching conditions cannot be derived with a variational principle. Means that energy is not variational. This may have some potential issues with the force or derivative calculations, other things. I believe derivative quantities in embedding theories are still very much frontier beyond tutorial. Usually there's no guarantee the matching condition can be satisfied, and usually there isn't a plan B. So fail. I mean, I couldn't do it. Despite all these drawbacks, the quantum embedding theories are often / widely, though not universally, viewed as one of the very few, and some people would even go to the only affordable way, but I think one of the very few is probably true, affordable ways to solve correlated electron structure problems. Some people may argue tensor network may do it, and here I have a comment at least before machine learning / quantum computing consumes everything. So that's the current perspective. There's some shared similarities to the domain decomposition methods for solving PDEs in applied math. But I want to say that they're fundamentally different because in solving heat equation, you always solve a thing in R3, let's say. This is like coupling Hilbert spaces of totally different dimensions. It's very, very different. It has some superficial similarities, but the similarity stops there. They also offer a particularly attractive alternative for material science we heard from the previous talk, and especially how to handle translational invariance. But I talked briefly about this in the opening day, and I won't talk about it here. But embedding or / some local version of correlated theories or so-called quantum embedding offers an alternative way and seems to be gaining popularity in terms of handling correlated electron structure for solids in general. The rest of the talk, the goals are modest. One is we want to understand why low-level solvers, let's say a Hartree Fock, I'm interested in an interacting system, why this low-level solver can provide any useful information for the high-level solver. It's just not obvious at all. Two is what's a matching condition, and when will the matching condition be satisfied under any circumstance, which is also not obvious at all. And because I think this is already enough for the talk, so I only focus on one embedding method, which is DMET. And this DMET is simpler than others to some extent, and also you can say a bit more concrete rather than saying, hey, I want to couple these two things together, let's hope it works, right? I mean, then it's still, I mean, the science happened that way, but hopefully we can say something concrete about these things. Any questions so far?
Yeah, Lin.
Yeah.
What is the computational cost scaling of the kind of quantum annealing or analog computational algorithms that aren't trying to find the exact solution, but an approximate solution relative to these high-level solvers?
We can talk about that later.
Okay.
Yeah, that goes to the quantum computing thing, a full lecture, yeah.
Okay.
Yeah.
All right.
So you were mentioning domain decomposition. So the matching condition would be the equivalent of some transmission conditions?
No, actually the matching conditions are not at all like that. That's why I say the analogy to domain decomposition just stopped there, which is I partition the global system into a few things, done. Right? The rest of the things just don't look like each other at all.
And so there could be different types of matching condition, or it's...
Yeah, there could be different, but all of them, they look pretty different from a Schwarz iteration, things like that. No. Yeah. Okay, so I'm going to talk about the MET. Why we talk about that? This is a method that Gardner Chan and collaborators came out about 10 years ago, and there are a number of papers on that, applications published in Science, so on and so forth. They're great. Just to show a few pictures. One is they're all for strongly correlated systems that DFT is very, very hard to get it right. And for 1D and the 2D Hubbard models, and at a reasonably large U, which is definitely in the strongly correlated regime, you see the energy per site goes pretty well, which is not that easy. Some of them are doped. Two is this hydrogen rain that we heard also in the past 2 days. You can stretch it. It goes from weakly correlated to strongly correlated. If you do RHF, energy go to the top of the roof. And but this one, the energy agrees pretty well with the fuzzy eye. Okay, so underneath there's a fuzzy eye. So it's not only saying that the qualitative feature is correct in the stretched limit, but it's actually on top of it. For this particular problem, not everything look like that. And this is the convergence of the energy. Very few DFT methods, or pretty much almost no DFT methods can show something like that. Okay, so the high-level idea of DMET is the following. I want to focus on the ground state, and that quantum system can be arbitrarily large in the sense that L can be large, NE can be large, number of electrons can be large. And a given fragment, you first show that it can only be coupled to a finite number of Bethe orbitals. I'm going to refine this statement. So I fix a fragment. I first show that there's only a finite number of so-called coupling things called Bethe orbitals. Yes?
I had a question regarding this Bethe orbitals. So you're modeling them as like harmonic oscillators?
I haven't defined them yet. I will define. Okay. 2 is that you try to obtain some information from this fragment plus Bethe called the impurity. And well, you remove some information from the low energy and high energy part. That's also what we saw from Dominica's talk. 3 is this Bethe cannot be obtained exactly, but you can iteratively update those. So let me first explain the high-level idea of so-called partitioning of the orbital space. You do a proper rotation. The proper is the key word. Then you will end up with these 4 things that appear ubiquitously in quantum embedding theories: fragment, Bethe, core, virtual. So fragment is just a part of the thing that has quartic interaction. Bethe is to be defined. Fragment plus Bethe forms so-called active space, means that there's a quartic interaction. Virtual and core, they're only quadratic interaction. Core means things are inactive because they are fully occupied. Virtual, they are inactive because nothing got populated. Of course, all these are approximations, but you do what you can. So now goes to the more mathematical part. How do you show there is, in principle, a finite number of Bethe orbitals? So the fragment, I just say use the index x from 1 to LA. LA plays the role of m I had before, just commonly in the literature. And the rest is called the environment from LA plus 1 to L. The general argument is something called the Schmidt decomposition, or numerical linear algebra called SVD, singular value decomposition. What it says is that you give me any fixed many-body wave function. Let's call this the exact ground state. I separate the degrees of freedom, the first LA degrees of freedom and the rest. I just cut it and do a SVD. Then I ask how many singular vectors can there be, and the answer is at most 2 to the LA, because it's limited by the degrees of freedom here. That's it. That's the proof. It might sound naive, but the important feature here is 2 to the LA has nothing to do with L or NE, which is your global system. And this is your exact Bethe. If you have access to it, you just do a projection, you will end up with almost like the exact thing you want, with some minor, some other things. So this U alpha is called a fragment orbital, V alpha called a Bethe orbital. These Bethe orbitals are really, really expensive, fully many-body thing. But the important thing is the number of those things is small. There are 2 main problems with this argument. One is V alpha, the Bethe requires exponential cost. And the 2 is that it can only be obtained with the information with the exact ground state, which means they're useless. So DMET's solution, or the recipe, is to construct some approximate Bethe orbitals from some non-interacting system. Go back to the thing I talked about at the beginning. Non-interacting system, or quadratic Hamiltonian, is one of the very few things you can actually say something about. And this is what they do. So I will demonstrate a linear algebraic derivation of DMET. It's probably different from any presentation of DMET you have seen before, if you have seen one. If you haven't seen one, this is the derivation. So, and okay, yeah. So this is based on something linear algebra called the cosine-sine decomposition. This is the linear algebraic statement. There are various versions. by Stewart in the early 80s. Zhao Junbai wrote a very nice thing in 1992 and summarizing this various versions of the CS decomposition is a purely linear algebraic statement. Q is a matrix, m plus p times k, has orthonormal columns. Here, for the reason that's of relevance to the discussion later, I assume m is smaller than k, p is greater than or equal to k. Okay? But there are other settings as well. So this matrix of orthonormal columns can be partitioned into Q1 and Q2. CS decomposition is the following statement. It's kind of weird if it's the first time you see it. This Q1, Q2 can be expressed as a unitary multiplied on the left. This unitary you want m by m, the size here. This unitary U2 is this thing, p by p, is the size of the row of Q1. Here you have 4 parts. Later, it will correspond to fragment path occupied virtual. Okay? So there's a C and S. These are diagonal matrices satisfying this rule. And because you can think this is cosine theta squared plus sine theta squared equals to 1. That's called the CS decomposition. There's a C and S, each of size m by m. There's some identity here of size k by k minus m. The rest are 0. And then you have a unitary here. If this is the first time you see it, this is really weird, and you don't need to memorize it. But I just want to say this is essentially what DMET does, or at least the most compact way for understanding what it actually does. So how is this related to DMET at all? Remember, the 1RDM is given by phi star. And phi is a matrix of L by number of electrons, NE. Then it has orthonormal columns. And I partition this into the fragment LA, and P is L minus LA, K is NE. Apply CS decomposition to it. You'll find the following. So there's a U1, which is m by m. I call it UA now. U2 is a p by p. I separate them into 3 parts, corresponding to these 3 guys. I just name them. This is LA by LA. This is LA by LA called UB, corresponds to a bath. This corresponds to that identity part called the core. This virtual corresponds to a 0. And I just corresponds to this part. I separate this V into 2 parts. Okay, it's a kind of hard to follow if you see it, but I just want to say you just apply a standard decomposition to your occupied orbitals. That's what I'm doing. So I said, these 4 things corresponds to the fragment, bath, core, virtual orbitals. Diagonal matrices sigma A and sigma B, the square sum together is an identity. Why do I call them fragment, bath, core, virtual? Especially why is it called core? Right? So because you just multiply that operation I just gave before, you end up, first of all, this virtual won't contribute to anything because it's 0. So virtual is gone. Virtual doesn't contribute to the density matrix, which seems intuitive. And core contributes only in this way, or you can write down phi dagger, you get this expression, and you have the D11, D12, D21, D22 given in this form. And here you can see that there is an idempotent part that's singled out. That's actually, in the rotated basis, will be decoupled from everything else. And that is why it is a core. It's inert. It's not coupled to any other orbitals. So, and virtuals don't contribute. Next, we will show specifically what I mean that the core doesn't contribute to the D. More specifically, this impurity, I cannot hope to get by solving the impurity problem, I cannot hope to get the entire density matrix right. It just have an impurity. The best I can hope is to get this D11 part right. If so, that is already enormous achievement, right? The thing I want to say is that the core orbitals don't contribute to D11. That's what I mean. Here's the linear algebraic proof. So we define the basis. actually this is a unitary matrix. And I don't need to use UA because there I can just, it's a square invertible matrix. I can just apply UA dagger. It will become identity. That helps for me to compute in the computational basis. The rest, I just put UB, UCore, UVirtual there as advertised. Then you compute the 1RDM in this rotated basis, which is nothing, literally a rotation. Then you will find that it block diagonalizes. The fragment is coupled to the bath. Core is the identity decoupled from everything else. Virtual is not coupled with anything. That is why when you worry about the D11, you only need to worry about these two. That corresponds to the active space picture I gave earlier. In fact, that active space picture will be exact in this sense if the system is non-interacting. In the physics terminology, only the bath part is coupled to the fragment orbital, but that coupled means this, means block diagonalization. The number of electrons in the impurity can do a simple counting. There are NE of those in total. And here you have NE minus LA, those number of things in the core. So the number of electrons in the impurity means fragment plus bath is NE minus the core, which is LA. In other words, this is the first a surprising statement from DMET, which says, in general, the impurity is always at half filling because the impurity has LA plus LA equals to 2 LA orbitals, and there are LA electrons, so it is at half filling. That's the linear algebraic proof. Does it make sense? Or this is already, whew.
So just to kind of see if I'm getting it right. So if the impurity is at the half filling, the rest of the electrons are then in the bath?
No, the rest of the electrons are in the core.
Okay.
In the core,
okay, yeah.
which is not coupled.
The impurity also
Right.
includes the bath.
Yeah, so this is the proof that, I mean, how come your system a fragment can be only coupled with a finite number of bath orbitals, right? The statement is that most of them, in fact, NE minus LA of those, they just aren't coupled with respect to the fragment at all. They still live there, but they can be handled by some other things. And and then you have a small number of those. You have to carefully select those so that they're coupled. Yeah. Yes?
Yes. Hi. So I get a little bit confused. So so far I have seen that you're using SVDs, and I mean, to my naive mind, it seems like you're basically considering it as a simple data structure. What I wanted to understand better is that, so coming back to the bath orbitals, how would be the physical intuition in the kind of quantum field? So I mean, what are these, like, how we write the field operators for those kind of bath orbitals? Because I can't understand what are those.
I won't be talking about field theory, but I will be talking about creation operators later.
But are we in second?
Just wait for 2 more slides.
Okay, thank you.
Okay. So, that's actually the answer is the next slide. So, what is the impurity Hamiltonian? So the impurity is fragment plus bath, and the impurity orbitals are this thing. So you have things in the computational basis. These are the UB that you found. The impurity Hamiltonian, hope that answers your question, is defined to be this way, which means that the BP are the first of them corresponding to the the first LA columns are literally equal to AP. The second LA columns, you obtain that through this linear combination. Then you define the impurity Hamiltonian to be this thing, HX hat, where this T tilde, the rotated quadratic matrix, is phi x dagger T phi x. Okay? Then you can prove that the 1 RDM corresponding to this impurity Hamiltonian gives you exactly the thing that you want. So that is why it is possible to reduce the dimension, solve a problem only of size 2 to the Lx, so that you recover the non-interacting limit. Of course, this is not advertised, this is not a suggested method if this is all you want to do, because you don't gain anything out of it, but there is consistency. And the exact derivation stops here. The next is the recipe part. The recipe is that for the interacting Hamiltonian, where you have this general, no impurity problem to start with, general quadratic plus the quartic thing, I focus on one impurity, x. I will move this impurity from one to the other. Remember, there are a few of them. And for one of the fixed impurity, I will define this partition via some non-interacting Hamiltonian, which is to be defined. How do I pick that? This gives a coefficient matrix T that allows me to get these orbitals. Now, the difference is that because this guy here, these core orbitals won't just be left out. They must also contribute something. The minimal thing you need to do is it contributes a Hartree-Fock embedding potential, electrostatics, and Fock exchange. And this is something that you need to do from here. And you also need to select another proper chemical potential to satisfy the hot filling condition so that, so this is, and the number of electrons is equal to LA. Let me describe how that works. The impurity Hamiltonian looks like this. It is of size Lx, which is 2La. The coefficients are obtained, there are 3 parts. Looks complicated, but it isn't. This is just written down the projection of T using the fragment plus bath. This is the projection of the quartic part with the fragment plus bath. This complicated thing is just the contribution from the Hartree-Fock with respect to the core. That's it. It's actually a very well-defined procedure. Again, if this is the first time you see it, it's a lot, but I just want to say it is in principle simple, and there is no obvious way to justify it other than saying this is a recipe. I do want to try my best to separate the recipe part and the thing that you can actually say more definitively. The non-interacting part you can say definitively. The interacting thing, this is what you do. Then how do you get your high-level 1 RDM, which is really the real deal that you want? You compute the 1 RDM, I call it P. Whenever you see a P, it really means D, but constructed from the high-level solver. And this is with respect to this new creation operators, BP, BQ dagger, BP, and we only trust the fragment part. And you just numerate all the fragments. You obtain diagonal blocks for all the 1 RDM for all of those things. And assume there are NF fragments in total. And the partition, they don't overlap with each other. And this gives you the diagonal blocks of the 1 RDM. This is the output, the most important output from the DMET. Other quantum embedding theories, they obtain similar things, but this is the output from DMET. Any questions so far? Okay. Issues not discussed so far. Each of them is obtained independently. The trace of that, hopefully, is number of electrons. How do I guarantee that? The answer is it won't be guaranteed automatically. So any equality should correspond to a Lagrange multiplier. So that Lagrange multiplier better appear somewhere. I'm not discussing that. 2 is how do you compute the total energy? That's an even more challenging thing. I only have this local thing, but I also know that the energy is global, and they need contributions from both the 1 RDM and the 2 RDM, the 2 particle reduced density matrix. And there's a recipe for that, and I'm not discussing that. So 3 is there are some special techniques. Orbital localization, we heard briefly from the previous talk. Charge self-consistency, non-interacting bath versus interacting bath, fragment fitting versus impurity fitting. I'm not talking about all those at all. There are a lot of recipe, a lot of moving parts that you can play with. So quantum embedding theory, maybe one take-home should be quantum embedding theory is not a theory. Even DMET is not a theory. It's just like a language containing many dialects or something. Yeah. So and they can smoothly transition from English to French in some cases, such as DME. The recent papers. I have specific examples. Recent papers of George Booth continuously connecting DMET to DMFT. So how do we iteratively update the bath and core orbitals? This requires some matching condition, which I will discuss in detail. This is the last part of the talk, which is, I hope, something that we can say mathematically, which is this glue part in the DMET. What's the matching condition? Is there any circumstance that the matching condition can be satisfied? Any question?
Just shortly. So when building together when stitching together the full density matrix, why do we ignore everything except for the fragment?
Because intuitively thinking, that's the only thing you can trust. There's no reason. That's part of the recipe. You can also...
But just like the way things are done.
Yeah, that's the way how this version, this dialect of DMET is done. You can come up with your own one.
Okay.
Yeah. Okay. So the matching conditions are stated as follows. So the low-level density matrix D should do two things. Remember, this D are supposed to be, we apply CS decomposition to its support and get to the fragment, bath, core, orbital, virtual. So this D should be chosen so that one should minimize some energy functional. It shouldn't be some just arbitrarily oscillating orbitals. It just doesn't make any sense. Two is that the diagonal blocks better match the diagonal things I have obtained, tried very, very hard to obtain from the high-level calculation. Why do you match that? That's part of the recipe. Okay, let's say this is our goal. So this matching 1 RDM blocks, as I said, whenever you say the word match, it means equality. When there's equality, there's a Lagrange multiplier. And that Lagrange multiplier is called correlation potential. It means that I want to stitch together a bunch of UX. Each is a dimension LA by LA. This just means a block diagonal. You have seen before. I get a block diagonal matrix called capital U. And I want to use this capital U to generate my D to match the high-level density matrix. Okay. More specifically, you give me a T, and that's the quadratic Hamiltonian, for example. I add this U, which is to be defined. I diagonalize, obtain the lowest NE eigenvectors. I obtain the D, so this D can be just written as a functional of T plus U with NE electrons. You give me T plus U, I have a matrix, I diagonalize it, I uniquely define a density matrix, assuming it's gapped. So T can be replaced by any fixed Fock matrix. It really doesn't matter. So as long as you have a way to justify it, that's part of the recipe, you're good. So now let's talk about the domain. We heard that Kiran asked, like, what's the domain of the green function theory? It's very hard to answer that question. But whenever you go to static quantities, somehow things are easier. And you can actually talk about the domain. The domain of everything we care about has a block structure which is Hermitian. For correlation potential, there's a gauge degrees of freedom because I can arbitrarily add a constant shift to the potential. It doesn't change the density matrix. So I need to modular that constant for example, without loss of generality, assume it's traceless. So that removes the degree of freedom from the trace. The high-level density matrix is this. So at least it should satisfy that the sum them together equal to NE, but also each block, the eigenvalues are bounded between 0 and 1 because it is a subblock of the global density matrix, which is bounded by 0 and 1. Okay, so these are the domains of the quantities. The original proposal of the DMET was this so-called least squares fitting process. I said there are two goals. One is to minimize certain energy. This is done with this functional. The second is the match. How do you match? Just match with the least square, like this. So I find a U, I diagonalize it, I project it, I see whether I'm off or not. If not, I take a derivative, so on and so forth. Okay? Very nonlinear optimization problem. A lot of local minimizers. You get stuck all the time. This right after this paper, Scuseria and the collaborators wrote this PRB paper in 2013, saying that in certain cases, guaranteed there's no exact matching. Therefore, they proposed a different method, which is called density embedding theory. That goes a lot like the OEP in designing exchange correlation functionals. But even for density embedding, there's no obviously you can match it. It just reduces the freedom a little bit so that you have a little bit higher chance in matching that, but the recipe is exactly the same thing. Gapless is a problem, which means that whenever you select a U, so that your T plus U has no gap between the NE and NE plus 1 eigenvalue, you're stuck. And actually, the whole thing is very, very hard to converge. This leads to a lot of numerical instability issues. And these three issues, nonlinear optimization with the local minimizer, inexact matching, the gapless problem seems to be some problems of independent importance. It's not obviously they're related to each other at all. They're just some problems, but this whole embedding thing has a lot of problems, so 3 more problems doesn't seem to be a problem. So that's the original philosophy. I want to say this is a problem. So you might think the impurity solver, which costs up to poly L exponential to the m, should absolutely dominate the computational cost. There's no question about that, because the rest is poly L, and in fact, it's L cube. How could that be expensive? This is what we worked on in 2019, so with Mike and Xiaojie Wu and a few and the Garnet Chan's group. So there's a high-level solver in the DMET, which means you're actually doing the impurity solving. There's a low-level part in DMET, which is dashed line, which is you're just doing impurity, doing the matching condition. That's it. Forget about this. This is a bit outdated, replaced by other methods. So this is just the LS DMET I showed you before. Indeed, as the number of size increase and the high-level solver becomes a bit more expensive, more and more expensive. But the low-level part, the cost increases pretty dramatically. And when you have not a very large number of size, which is 128, the time for the low-level part just doing the matching is 20,000 seconds. It's even more expensive than the high-level part. So that is a real problem. And so it means that this matching condition, when you try to achieve self-consistency, is something you should really worry about. 2 is another 2D model, 6x6, but now I add a little bit of random potential, on-site potential, and in the phase diagram. And this is the fitting, and this is the U. Fitting means the number of electrons divided, the ratio between the number of electrons with L squared, the number of size you have, with L, the number of size you have. And U means the interaction strength U. And you can see that in some cases, fitting here, the success rate is pretty close to 100%. Here, the success rate is drops like to around 0%. And so just there's no exact fitting. And you either got stuck at the local minima or reported there's a gapless problem or some other things. So this is a real problem. And we discussed a lot with Gardner and say, whenever this problem happens, you try to change things a little bit, make the problem slightly larger, still keep the ratio around that. I mean, so on and so forth. There are a lot of tuning that you need to do to make things work. And then we thought about whether you can reformulate the fitting problem to make this something a little bit cleaner. And this is the, we first look at the energy functional, and which is this FU. This FU is defined to be the sum of all the eigenvalues below the chemical, the first NE eigenvalues of this matrix T plus U. You give me a U, I compute the energy. So this is equal to trace T plus U times the corresponding density matrix. This is the same story as in the non-interacting system. When this is gapped, means that you have a gap here. Then a nice thing is that the gradient of the functional with respect to the correlation potential, or this Ux, gives you exactly the density matrix block you want. So what you want to do, essentially, is to match the gradient of this functional with respect to some given number. It's a nice thing you have. This can be derived with a Feynman-Hyman-like argument. It requires a few lines of derivation. This FU functional is also concave. It actually will play an important role because where I'm getting is that if you formulate it as a least square problem, then it is not a convex optimization problem. You can get stuck at local minima. But if you can reformulate it so that it becomes a convex problem, then you're good to go. Okay? And convex and concave differ by a sign. So this concavity can be proved with two lines. You just plug this alpha U1 plus 1 minus alpha U2 into that, and you pull the alpha out, and you will find that the density matrix is the non-optimal one. This one has a lower energy, and you just sum them up, and you will find this relation. So it is a concave functional. Since it is concave, and you can define the so-called concave conjugate, and this is mathematically called the Legendre-Fenchel transform. And so this is really Mike's idea, that you look at the dual of it, that is this F star P given by the standard Legendre transform. So you have some inf of the becomes inf of the correlation given this high-level density matrix called P, and here is your U, the correlation potential, minus FU. Remember, given any U, I can define this sum over the lambda, and now you define the dual of it. This problem, if can be solved, just gives you U, period. And you can find correlation potential with this way, with the convex or concave optimization using off-the-shelf software like CVX, robustly find the global minima. This is the code. This is short. Of course, you need to put a few bells and whistles around it, but this is the idea. You CVX begin, you set the variable as a real symmetric or Hermitian, subject to minimize U times P given P minus lambda sum smallest, means sum over all the eigenvalues, T plus U, and E subject to U dot mask equals 0. Mask is give you mask sparsity pattern. That's it. This is the code. And it will find correlation potential with no local minima. Here's how it works. The left, remember, it goes from 100% to 0%, and this case doesn't work. On the right, Still, there are a few spots that doesn't work so well, but here it's like 100%. But even when it doesn't work, it's like 90% of successability. This is 0%. So yeah, this is a paper we had like 2 years ago on PRB. You can also, that solves the problem 1 to some extent, which is the numerous local minima issue can be solved at least somewhat by this convex reformulation. We still have 2 problems that seems to be unrelated. One is when you can have exact matching. 2 is sometimes it becomes gapless. This is, to our knowledge, the first time that connects the 2 issues together with a theorem. So the theorem says this. You need to make an assumption a little bit stronger, which is P is given not only just bounded between 0 and 1, but it cannot reach 0 and 1. Otherwise, you have some bad cases, corner cases. And then the evaluation of this dual functional always admits an optimizer. I don't know whether it's unique, but there's an optimizer called U star. And this P technically lies in the so-called supergradient set of F du. This sounds technical, but what it says is that if it is gapped, then this supergradient becomes a gradient, which means exactly you have exact matching. Remember, the gradient of F, when it is well defined, gives you the diagonal of the block. P lies in that supergradient means that you have exact matching. So what it says is, if F plus U star is gapped, then this guarantees that you yield exact matching. If this gapless, with this additional assumption, if the correlation potential is also unique, then provably the exact matching is not achievable. But the provably is actually only 2 sentences. Some remarks, and this is a technical remark, which is that there are 2 technical remarks. One is that this condition ensures that this is in the so-called relative interior of the domain, and that allows you to take this supergradient. And the second is that the condition for U star to be unique is so far open question. We don't know how to characterize that. We don't know when it is gapless or even gapped, whether there are other solutions. So what to do with the gapless problems? The first, we wrote this paper, we're very happy, thought the problem is done, the matching, we move on. But the more applications we do, the more we found that this gapless issue really arises more frequently than you like. It occurs in some totally benign and you can say innocent quantum systems. I have 2 minutes. For example, Hubbard model. And this is the problem we found that both the LS DMET and the CVX DMET assume the so-called Aufbau principle. You fill the electrons 1 by 1. Let me just skip this thing and just ask, is there a way to skip the Aufbau principle to yield the exact matching? And I believe this is Fabian Faustich, and is going to give a talk on this in workshop 1. I won't talk more about that. Just want to say that this Aufbau principle can be violated in some rather trivial regimes. I have some hydrogens. I just gradually open them. And the couple cluster and the MP2 energy, their curve is very smooth. But some places, the DMET, assuming Aufbau principle, will yield a gapless problem. And it will get inexact matching. And the reason is because the exact one violates the Aufbau principle. This means the 1, 2, and the 5th orbital is occupied. And this is the 1, 2, and the 7th orbital is occupied. Why is it like that? I don't think there's any chemical intuition. But this is what the optimizer tells you to do. Conclude. So quantum embedding theory is not a beautiful theory, but it's a scalable way for doing legitimate correlated electron structure calculation. And if there's no miracle to make machine learning / quantum computing / PEPs to work in the near future, this is probably the only way that I'm aware of. We can debate. Involves recipes or artistic components that you can have a lot of room to work around. You can definitely come up with your own embedding theory in this workshop, and maybe they will outperform all other previous attempts. Energy is not variational. There are some recent exceptions that I believe Mike is going to talk some of this in workshop 1, not the tutorial talk later this week though. Matching condition in all flavors. I only talk about the DMET, but DMFT, some other things, deserves careful mathematical scrutiny. And there's room for both algorithmic improvements. It's not just you prove that it works, it doesn't. And at least in some cases, it's not even corner cases, just happens when we open. Which may actually impact practical quantum embedding theory calculations. So this is the right time to do it. And I can also talk about DMFT or other things later in the program if there's interest, but I think Dominica already gave excellent talk. I can give a more mathematical flavored thing if there's interest. Thank you for your attention.